Isaac Berry from Berry Science Lab, and welcome to Quantum Mechanics.
All the way from there.
Welcome to Quantum Mechanics, Lecture 1. So today we'll just get started with the basics of quantum mechanics. What do we call objects? Well, in classical mechanics, we start with a ball. Maybe this ball is constrained to one axis because that makes things simpler. So let's say it's only moving along the y-axis. And its motion is going to be defined by some initial conditions, as well as, actually it shouldn't be x in this case, it should be y. It's determined by these, as well as some potential function of distance, it's actually y, and time. So, what is this potential function? Well, in the case of this ball, it's mgy. So then, how do we calculate the motion of this ball from these three essentials? Well, it all comes down to Newton's second law, which defines the entirety of the Newtonian formulation of classical mechanics. F equals ma. What is F? The negative of the derivative of the potential with respect to distance. What's this side? Well, it's the mass multiplied by the double derivative of position with respect to time. So now, what happens if we plug in this situation? Well, we get minus partial u partial y. What is this? mgy. So minus partial u partial y is just going to be minus mg. And that's equal to n d squared y dt squared. So it's actually not all that hard to solve for this in our case. We just get that d squared y dt squared, the acceleration, is expected is equal to negative g. So what does that make it? What does that give us? Well, you integrate once with respect to time and get gt plus c1. And then you integrate again with respect to time and you get half gt squared plus c1t plus c2. And as you can probably guess, these are determined by our initial conditions. Now, quantum mechanics takes a look at that and throws it out the window.
No, don't erase. We're gonna go this way.
Sure. Well, quantum mechanics effectively, if I'm not erasing it, quantum mechanics effectively is. In quantum mechanics, there is no such thing as the position function of our ball anymore. We don't have a concrete position for our ball. The main object of quantum mechanics are these things we call wave functions. So what are wave functions? Well, they seemingly have no meaning. They just look like regular functions of position and time. However, Bohr's statistical interpretation makes quantum mechanics transition from a hallucination to an actual physical theory. This tells us that if we integrate this with respect to distance at a certain time, from point A to point B, and actually it's not this, but it happens to be this squared, then this gives us the probability whatever object is being described by this wave function is between points A and B. And that's just because we're integrating over the interval a comma b, which is how all 2D integrations work. Of course, this also works in 3D, just you're integrating over a rectangle instead. So, this essentially works as a probability density function. Now, let's review a few things about statistics that we might want to know. First of all, if you integrate this from negative infinity to infinity, what should be the expected result? Well, something that's integrated from negative infinity to infinity and gives you the probability of an object being between those 2 points
Is 1.
Yes, because it has to be somewhere on the spectrum. It's 100%, which is just 1. Otherwise, our object doesn't exist. So if we integrate over the whole thing, this has to be 1. But how do we know Schrodinger's equation is actually compatible with that? I mean, it doesn't have this normalization included within it. Well, it turns out Schrodinger's equation actually satisfies linearity, which means that if phi is a solution, c multiplied by phi is going to be a solution too. So, there goes the problem for us. And of course, you might ask, well, what happens if this is changing over time? Then of course, its magnitude squared is going to be changing over time, and then it might no longer be 1 from negative infinity to infinity. Well, Schrodinger's equations actually auto-normalize for us, and we'll cover how that works next time. But for this time, we'll cover a few more statistical basics before we finish. First, we have the expectation value. Now, the expectation value, as you might guess, is kind of like the expected value you might have learned about in probability. You're just taking this function's average value in order to guess where the particle is most likely to be. Now, of course, that doesn't always mean the particle is exactly at this point. To take an analogy, let's say you have a 14-year-old and a 20-year-old, and what's a number that would fit nicely? A 36-year-old, all in one room. Don't ask what they're doing with the teenager. So, what's the sum of these three? Or, well, what's the average of these three? 34 plus 36 over 3. So that gives 70 over 3, which is about 23.33. But do you see a single person in here who's 23, let alone 23.33? No. So, in the same way, a function or a particle might not always be where its expectation value suggests it will be. And one more thing, the strangest thing about quantum mechanics is that things are changed by measurements. What are measurements? Well, we still don't really know, but whenever we ourselves observe an object, we of course, so we ask the computer where is the object, and it returns, let's say, some position, point A. Then you have to ask, what was it doing before then? Because, as we know, we can't ever exactly know where this particle is by Schrodinger's equation. We only have this wave function, which suggests its most likely point to be in, and the average value of the probability density function gives us, well, the average of all possible positions it could speed. So, this computer has to give us one value, yet we know that what the computer is observing behind the scenes can't have just one value. And therein lies the question. Does the particle somehow know?
1 second. My phone died.